Thanks for coming to my talk. I'm going to talk about some work that I've been doing with my co-author Neil. Okay, the problem we're trying to solve here is this. We know how to extend a purely functional language with monads to encode effects. What we want to do is to extend an impure functional language and encode the absence of effects. Okay, well, as the title says, we're going to use Comonads to do it. But why do we care about this problem? Well, okay, let's say we have an impure functional language like OCaml, and let's say I write down the map function, which maps a function over lists. Okay, this is the usual way you would do it. And then I could also write it in a tail recursive way. And well, these two functions should be equivalent observationally, but they're not because we can do side effects. So if I had an identity function which prints the string before returning it, these two functions would behave differently because the evaluation order is different. All right. Besides that, consider the map function. If I apply it twice, so map1f applied to map1 of g should be equivalent to map of f compose g, but that doesn't hold. So we've lost all static guarantees about map being a functor. So we lose useful things like referential transparency and all that. So is there a way we can recover all of that? Well, I'm going to show you how. So what I want is to write down a type signature for map where I say that the function that I pass into it is always going to be pure. So I want to add a pure type constructor to my type theory. Okay. Well, the first observation is that pure is a comonad because it has a co-unit and a co-multiplication. Okay, so all we need to do is extend our type theory with a comonad. So we're going to use an old idea from Fenning and Davis, which is about how to reconstruct S4 modal logic using judgments. So we're going to make a modal type theory where purity is a comonad. Okay, so let's start with an impure call by value lambda calculus. Okay, so it has okay, so it has units, products, and functions, and there is a print statement which allows you to print strings on channels. I'm going to use the type cap here to represent channels. Okay, since it's an impure language, we have to distinguish between values and expressions. So values are all of these, and the remaining ones are not values. Okay, so we will extend this grammar with the following. So I add a new type called box of A, which says that A is pure. The box has an introduction form and an elimination form. A boxed expression is a value, okay? And I also have to distinguish between pure and impure values or expressions in my context. So so variables in the context will take a qualifier where the red thing means that it's impure and the blue thing means that it's pure, okay? Now let's look at some typing rules and how we change them, okay? These are the usual typing rules from the lambda calculus for functions, and this is a print statement which, since the calculus is impure, returns unit. Okay, so now the variables in the context have the annotation Q, which means they could be pure or impure, but functions are impure. Okay, and we need to give rules for the pure type constructor. Okay, so the pure type constructor is introduced in the following way. If we know that the context is pure, then we can put an expression in a box and it becomes a pure type. And to eliminate pure types, we need to make sure that we only allow pure values to depend on pure things in the context. Okay, and finally we need this pure operation which we used here on the context, and the pure operation simply drops the impure values from the context. Okay, okay, and let's also try to look at the equational theory. So the functions in the impure lambda calculus have a beta and eta law. The beta law only allows you to substitute values for variables, and the eta law allows anything. Okay, in the impure when we extend it, we'll allow two kinds of eta rules, and one allows you to extend eta expand on pure for pure expressions, and the impure one only allows it for values. Okay, so with the syntax, and also we also have to extend the beta laws to include the box type constructor, and we also separate them out for impure and pure. Okay. And finally, this is just syntax. It doesn't mean anything. So let's give some semantics to it and see if the syntax is actually good. Okay. So I'll sketch a very briefly a categorical semantics for it. So We take the normal semantics with sets and functions, but we track the information about what kinds of capabilities the functions are using. So the objects of my category are going to be sets where there's a weight function which assigns a subset of capabilities to each set, to each value in the set. And we only allow those functions for which the function only allow those functions which preserve x. Okay, so the weight of f of x is a subset of weight of x, so it cannot use any other capabilities than the ones it was passed. Okay, it turns out that this category is Cartesian closed. It has products and exponentials. Okay, so we can already interpret most of the lambda calculus into it, but we need a monad and a comonad to interpret effects and the absence of effects. Okay, so we add this comonad box on it. The comonad says that you cannot perform any effects. And we add a monad T on it. The monad T tries to track which effects are being performed, whether any effects were performed. And it turns out that this monad and the comonad have a distributive law, and the comonad cancels the monad. Okay? So with this semantics in hand, we can try to interpret our syntax. So we interpret types, the usual units and products, but functions are allowed to have effects, and the pure type says that they're in the comonad. And with this, we can finally interpret our judgments, and this gives us sound semantics for it. We can show that we have substitution for this calculus. Substitution is sound syntactically and semantically, and we also show that the equational theory is sound. Okay? Okay, so finally, with all of this machinery, we are going to try and recover purity in this. So what we are trying to do now is that we will give a translation from the pure call by value lambda calculus into our calculus. We follow the usual translation by Girard of call by name. And so we translate A arrow B to box of A arrow B, where we restrict the domain so that it doesn't allow you to perform any effects. We do context and terms appropriately by adding a pure annotation on it. Okay. And finally, we'll notice that this embedding will preserve the equational theory of the lambda calculus, and the embedding is faithful. Okay, so this is what it means technically to preserve purity. And finally, with all of this technology, we'll go back to our previous map example, and all we have to say is the map takes a box f and apply the box on the right. And this function is guaranteed to be pure and satisfy all the things that we wanted. Okay. And that's all I had to say. If you want to read more details about what's going on, we have a paper on the archive where everything is worked out in much more detail. Thank you.
Okay. We have time for one question while Ryan gets set up. So would it be possible to infer the box annotation that's needed there in the map term that you wrote from the type annotation?
From the type annotation? Yes, since the only introduction rule is box, but you don't have an eta rule for it. So no, but if you could statically, since it's polymorphic, yeah. But if you know the types and you know their pure types like integers or strings, then yes, you'd be able to infer things.
I mean, if you just wrote map without the box in it, is it possible to read from the type where the box
yes,
constructor and pattern need to go?
Right. So I think you'd have to analyze the things on the right and make sure that there's no print statements on the right. Yeah. Then you'd know on the left. I could use the box. Yeah.
Okay. Let's. Okay, and